So till now we have spoken about ANOVA, why ANOVA is to be used, when to use t-test, when to use ANOVA. T-test is used when there are two population or groups, and ANOVA is used when there are more than two groups or more than two populations. So we also saw the assumptions of ANOVA, and we discussed why post-hoc test is necessary in ANOVA. Now we are going to run the first ANOVA exercise or the ANOVA test in SPSS. The objective for this particular test is they are given a depression score. They've also given 4 different types of treatments that the patients are undergoing. So the 4 different types of treatments are the 4 independent categories, okay, or the independent variables or the factors. The depression score is the dependent variable. So we are going to check if there is a significant difference in the means of the depression score among the patients who have undergone the 4 different treatments. Okay, so the dependent variable is the depression score. The independent variable is the treatment or the medicine. So I will just stop sharing. I want all of you to go into your SPSS and open the particular file. So is my SPSS file visible?
Yes, ma'am.
Right, thank you. Okay, so here you see there is an ID. It could be a patient's ID or it could be some ID given by the organization. Then you have the gender. Then you have the birth date. Then you have BDI. So BDI is the depression score. Okay, it is the Beck's depression score. So that is a particular scale by which the depression is measured. And so the depression score is measured. See, it's a running number. It's a continuous running number. So it is called as it is suitable for a dependent variable. Then you have the BDI group. Okay. Then you have the medicine. So in medicine, you have 4 different types of medicines. So when you go to variable view, okay, when you go to variable view, you click on the values. So you find that 0 is male, 1 is female. Okay, 0 is male, 1 is female. Then when you click on the medicine, so 1 means none. None means no medicine is given to the particular group of candidate, to that particular group. 2 means placebo. Placebo means there is no actual treatment given, but they just give some kind of empty tablet so that they will feel that they are taking something. So that is called as a placebo. The third one is homeopathic, and the fourth one is pharmaceutical. So these are the 4 different types of medicines or treatments that is given to different group of patients. So now we are going to run ANOVA. So to run ANOVA, whenever you see a data set, you first understand what are the different columns in the particular data set. Try to see what will have a relationship with what, or how each can be linked to each other. That will give you a better understanding of how to decide what test has to be done for this particular data set. So going to analyze, compare means, the last option is one-way ANOVA. Okay, analyze, compare means one-way ANOVA. Click on one-way ANOVA. So those who are having the system, kindly start doing along with me. If you feel that I am going fast, kindly stop me. So go to analyze. So the data set taken for this particular exercises, the name itself is given as ANOVA file. Okay, the name itself is given as ANOVA file. So we are working on the ANOVA file currently. Okay, so now the score on Beck's depression inventory. So this is the dependent variable because we are going to compare the depression score between different groups. So this is the score on Beck's depression inventory. Now, what is the factor? Factor is the different treatments given. Okay, so that is the medicines administered. Okay, that is the medicines administered. So the medicines administered should come under factor, and under the dependent variable, score on Beck's depression inventory should come. Then contrast, you need not click. Go to post hoc. So in the post hoc box, click on Tukey. Okay, in the post hoc box, click on Tukey. Then say continue. Okay, there is Tukey and Tukey B. You click on Tukey. Then going to options, we want descriptive. Then we want homogeneity of variance test. Remember, one of our assumptions was homogeneity of variance between the groups. Okay, so to test that, this particular box has to be checked. Okay, so this is called as homogeneity of variance test. Click on continue, click on OK. Can I click on OK, or do you have any doubts? Can I click on OK and continue?
Yes, ma'am.
Right. So I'm clicking on OK. Okay, so I will share my output. So this is the output. Now is my output visible?
Yes, ma'am.
Okay. So now you see here, the first table is the descriptive table, because we have asked for descriptives. It has given us a descriptive table. It shows here in this particular table, the third column is important. Okay, the third column, mean column, is important. What is the mean mean? It means that what the average depression score among the particular group of patients who are undergoing treatment. So among the patients who are not undergoing any treatment, the depression score is 41.72. So for those who are undertaking placebo, it is 35. For those who are undertaking homeopathy, it is 35. For those who are undertaking pharmaceutical treatment, it is 26. So you find that different group of population have a different mean score. Now we cannot conclude by just seeing at the mean score. We also have to see, okay, we also have to see the ANOVA table to conclude. So before going to the ANOVA table, let us see at test of homogeneity of variance. So what it actually means, the variance should be homogeneous among different populations or different groups. So if you want the groups to have an homogeneous populations, then your null hypothesis should be accepted, right? Because your null hypothesis will always be homogeneous or equal. Okay, so when will you accept your null hypothesis? When your p-value is greater than 0.5. Okay, when your p-value is greater than 0.05, sorry, 0.05. So here in your test of homogeneity of variance, you find your significant value. Okay, so this is the significant value. Do I have a pen somewhere? Okay, pen is not there. So this is a significant value, 0.949. So this 0.949 is greater than 0.05. Hence, it is concluded that there is homogeneity of variance in our data. Okay, there is homogeneity of variance in our data. So the assumption is supported. Okay, the assumption is supported. So next, let's go to the ANOVA table. So in this ANOVA table, you have to see the significant value. So the significant value, okay, before going to this, what is your null hypothesis? There is no significant difference in the means, correct? There is no significant difference in the means of the different groups of treatments in with regard to the depression score, okay, with regard to the depression score. So that is your null hypothesis. Here your p-value is lesser than 0.05. If it is lesser than 0.05, your null hypothesis gets rejected. Okay, if it is less than 0.05, your null hypothesis gets rejected. So your alternate hypothesis gets accepted. What is your alternate hypothesis? There is a significant difference. Okay, there is a significant difference among the various groups of treatments with regard to the depression score. So now, after concluding this, go back to your descriptive table and see your means. So here you see that for none, the depression score is very high. For pharmaceutical, it is the least. Okay, so after you interpret your ANOVA table, your mean gives you more meaning about which group has more depression score, which group has less depression score. Next, coming to your post hoc test. So your post hoc test, pay attention. So here in this first column, you have none with placebo, none with homeopathy, none with pharmaceutical. Then the second one with the remaining three, third one with the remaining three, fourth one with the remaining three. So here also to find out whether these two groups are different in terms of their depression score, there is in the fourth column a significant value. Okay, in the fourth column, there is a significant value. So here the p-value should again be lesser than 0.05. If it is lesser than 0.05, then between the two groups, there is a difference. Okay, between the two groups, there is a difference. So here you find that there is a difference between none and placebo, none and homeopathy, none and pharmaceutical. In the second row, you will find that placebo and none have significant difference. Placebo and pharmaceutical have significant difference. Placebo and homeopathy does not have a significant difference. Okay, is it clear? Do you want me to explain further?
It's clear, ma'am.
Right, thank you. So the last table here tries to tell you how they have classified these depression scores into three groups. Okay, so the 26.88 is falling under one group. The 35 and 35 score is falling under another group, and 41.72 is falling under another group. So they are trying to say we can classify these entire four groups into three groups. And pharmaceutical is the least with the depression, and none is the highest with maximum depression. Placebo and homeopathy seems to have a similar depression score. Okay, similar depression score. Now, when you are writing your interpretation, what are the values that are important? So in your ANOVA table, okay, in your ANOVA table, the degrees of freedom between the groups and within groups is important. The F value is important. The significant value is important. Okay, so these are the four values that you will have to write. Then after interpretation of this, you have to talk about the mean score of depression between the different four groups. Then at the last, you should say which group and which group are having a significant difference. Okay, so I hope it's clear. I'm going to go back to my PowerPoint. Okay, so how we did this? Analyze, compare means one-way ANOVA. So Tukey test, you have to click. Then descriptive homogeneity of variance test. So this is the various tables that we got there. So now let's see the interpretation. There is a statistically significant difference between groups as determined by one-way ANOVA. So F followed by 3. What is this 3? 3 is the degrees of freedom of the first one, followed by degrees of freedom of the next one. Okay, so between and within. So that's 3 and 96, which is equal to the F value, which is 20.732, and P is lesser than 0.01. Okay, lesser than 0.001. So this is the first interpretation. Second, you should say, a Tukey post-hoc test revealed that the depression level was statistically significantly different between the groups. So none with others was completely different. Pharmaceutical with others was completely different. Then you can also talk about the mean score of none, mean score of pharmaceutical. Okay, mean score of none and mean score of pharmaceutical. So with this, Anova test is complete. Do you have any doubts?
No, ma'am.
Okay. So now let's go to the next test, which is called as two-way Anova or factorial Anova. Okay, so what is this one way? What is this two-way? For example, when you have one factor and you are trying to see whether that particular factor is different in the groups. Okay, so then it is called as one. Okay, I'll come again. So in the previous example, we took treatments. Okay, we took treatments and we wanted to see whether there is a change in the depression score. So the treatments is one categorical variable, which has 4 different groups, correct? Which has 4 different groups. Now, along with these treatments, I also want to see whether gender is also different, whether the depression score is also different among the genders, or whether depression score is also different between the different age groups. So again, I am taking one more categorical variable in my study. So when I have 2 different categorical variables as independent variables, and I have one continuous dependent variable, then it is called as two-way Anova. Supposing I have more than 2, okay, I have more than 2 categorical variables. I'm not talking about groups, I'm talking about variables. Variables has groups within that. Okay, variables has group. For example, treatment is a variable, then gender is a variable, marital status is a variable. So these, within this, you will have different groups. So if you have more than 2 variables as your factors or as your independent variable, then it is called as factorial Anova. Okay, it has factorial Anova. Factorial Anova has n number of independent variables. Okay, factorial Anova has n number of independent variables. So now we are going to see one factorial Anova with interaction effect. So let me tell you what is interaction when we go to that. So you understood what is factorial Anova. If you have more than 2 independent categorical variables, then it is called as factorial Anova. So factorial Anova, instead of repeating, so otherwise what I have to do? First, I have to do one Anova with treatment and depression. Second, I have to do another Anova with gender and depression. Third, I have to do another Anova with age group and depression. So instead of doing different Anovas, I am trying to club all my independent variables together. Thereby, I can also see whether there is an interaction between the variable. Okay, there is an interaction between the variable. So here, what are your assumptions? So some assumptions are common with that of Anova. Some assumptions are new. So let us see. So first one is dependent variable should be a continuous variable. Independent variable should be a categorical variable. Okay, independent variable should be a categorical variable. There should be independence of observations, no outliers. Your dependent variable should be normally distributed, and there should be homogeneity of variables. All this I've explained. So you have the same set of assumptions as for Anova. Now, what is your format? Okay, what is your flow of how you should do a factorial ANOVA? So first, you should run a two-way ANOVA, and your sample size between the groups should be roughly equal. If it is not equal, then you have to do a Levin's test. So if the Levin's test is statistically significant, then you can rerun ANOVA and interpret Welch statistic. If it is not significant, you can directly go to the interaction effect. Okay, you can directly go to the interaction effect. So from the interaction effect, if it is statistically significant, you can rerun ANOVA with simple effect. So in this simple effect, if your main effect is statistically significant, then you can go to the end of ANOVA and perform the post hoc test. Okay, you can perform the post hoc test. And next, if your post hoc test also gets results, then you can complete your ANOVA. Okay, so here you are seeing a Levin's test, you are seeing an interaction effect, you are seeing a simple effect, and you are seeing a main effect. Then you are seeing a post hoc test. Do not get confused. See, like how we check boxed and we got this homogeneity of variance. Same way, Levin's test is also one of the output tables which we can easily interpret to find out whether the sample size are equal. Okay, whether the sample size are equal. Okay, so the sample size will be equal when it is not significant, when the p-value is not significant. So then we have to do an interaction effect. And if the interaction effect is significant, then we have to do a simple effect test. Okay, then you can, from the simple effect test, you can find out what is the main effect, whether the main effect is statistically significant, then perform a post hoc test, etc. So it sounds quite complicated, but it is not very complicated. It is very simple. We will be doing it shortly. So here we are going to perform a factorial ANOVA. So there is no significant difference in the means of the depression score due to the interaction between gender and medicine. Remember, we performed an ANOVA test sometime back where we used medicine as the categorical variable and depression score as the dependent variable. Now we are going to use, along with the medicine categorical variable, we are going to use a gender variable also. Okay, we are going to use a gender variable also. So we are going to use two independent variables and one dependent variable, making it a two-way ANOVA. Okay, so how to run this two-way ANOVA or factorial ANOVA? You have to go to Analyze, General Linear Model, Univariate. As long as your dependent variable is single, you have to use univariate. When your dependent variable becomes more than one, then you have to use multivariate. Okay, then you have to use multivariate. Okay, right. Now let's go to general linear model univariate. Then we have so many other things that we have to do. I will tell you one by one we can perform. Okay, so I'm quitting this PowerPoint and I'm going to go to Anova file, which we already have it open. So can you see my SPSS screen?
Yes, ma'am.
Right. So let's go to Analyze, General Linear Model, Univariate. Okay, General Linear Model, Univariate. So what is your dependent variable? Score on Beck's depression inventory is your dependent variable. Medicine administered is your fixed factor. Gender is another fixed factor. Okay, model contrast we need not touch. Go to plots, horizontal, gender, separate lines, then click on add. So you are trying to create an interaction effect between medicine and gender. Okay, then we can also try out gender, medicine, add. Continue. Go to post hoc. Do the post hoc test for medicine. Tukey. Continue. Okay, I'll go and put even gender. Options. So all the three. Display means, descriptive statistics, homogeneity test. Okay, so these are the ones that has to be ticked. Okay, did you follow? Do you want me to repeat and show you? Can I move forward? Yes, no?
Yes, ma'am. Yes, ma'am.
Right. So continue. So click on OK. Okay, so here the first table shows you what is the different numbers within the particular group. Okay, so none, placebo, homeopathy, pharmaceutical all have 25 each. Male is 46 and female is 54. Next, coming to descriptive statistics table, it shows the breakup.
Madam, output is not visible, ma'am.
I'm sorry. Okay. Is it visible now?
Ma'am, yes, ma'am.
Right. Okay, so this is the output for this particular factorial ANOVA or two-way ANOVA. So here the first table shows you the number of participants within the particular group. Okay, number of participants within the particular group. Then the second table shows you within the groups. Okay, within the groups, what is the mean value? So if no medicine was administered and the gender was male, then what is the mean value? And if no medicine was administered and female is the gender, then what is the mean value? So you see in all the tables, female seems to be having a higher depression score when compared to the males, except in the case of pharmaceutical. Okay, except in the case of pharmaceutical. Is it clear from this table? How I'm finding out from the mean value. So in the first table, you see males having 37, female having 45, like that. So you see the mean is always high for females in all the different administered medicines, except in the case of pharmaceutical, where females have 25 as a depression score and male have 29 as a depression score. Okay. So next, coming to Levin's test of equality. So see here, your p-value is greater than 0.05. If it is greater than 0.05, it means there is equality. Okay, that why we are doing this, to find out whether the sample size is more or less equal between the different groups. The sample size is more or less equal. That is why you have got a significant value which is greater than 0.05. Okay, so the next table is test of between subject effect. So now here you have to see the first column you see after the second row, that is corrected model is the first one, intercept is the next one, third one is medicine, fourth one is gender, fifth one is medicine into gender. So medicine into gender is the interaction effect. Okay, medicine into gender is the interaction effect. We will be using pen. I do not know where the pen is. Okay, fine. So for all these three, medicine, gender, medicine into gender, just a minute. Sorry for the interruption. Can you hear me?
Yes, ma'am.
Yes, ma'am.
Okay. So here you see medicine, gender, medicine into gender. Okay, for all these three, check the significant value. The significant value should be lesser than 0.05. Okay, for medicine, it is lesser than 0.05. For gender also, it is lesser than 0.05. For medicine into gender, this medicine into gender is called the interaction effect. Okay, it is called the interaction effect. So that is also less than 0.05. What does it mean? It means that medicine the different groups of medicine have a different depression score. Then gender, the different gender have different depression score, or there is a significant difference in the means of the in the means of the depression score among the different gender and among the different medicine treatments. The last one is medicine into gender, which is a interaction effect. So the interaction effect is also significant. Okay, the interaction effect is also significant. So what all you should take for writing your interpretation, your F value, your significant value, and your degrees of freedom value. So the degrees of freedom, you should take that particular degree of freedom, comma, the degree of freedom of error. That is 92. So like that you should write. So I will tell you for one, how to write. As per the test of between subjects effect, there is a significant difference between the different there is a significant difference in the means of the depression score among the different medicine, among the different groups administered with different medicines. Within bracket, F value, you put F, within bracket, write 3, 97, close the bracket. F value is equal to 22.842 and P value is lesser than 0.001. Okay, so like this, you have to interpret each 3 lines separately. Then coming to estimated marginal means. So here it shows you the mean value of the different medicines, the mean value of the different genders. Then it shows you within the particular medicine, what for male, how much, for female, how much. Based on this only, we interpreted earlier also. Now coming to the post hoc test. So see the post hoc test, see the significant column. Okay, see the significant column. The significant column is less than 0.05 for none with all, with pharmaceutical with all. In the case of homeopathy and placebo, they are significantly different from none and pharmaceutical. Okay, so this is how you should interpret. Now see this particular graph at the bottom. You find that this doesn't make meaning. See this. So for male and female, how it is varying. Okay, for male and female, how it is varying. Similarly, the first table also, you find that a green line is a female line. So you find the depression score 45 for none or more than 45 for none. And for pharmaceutical, it is coming as low as 25. Okay, so you find the difference between the different treatments. You also find the difference between the different genders with regard to the depression score. Okay, with regard to the depression score. So like this, you have to interpret the table. Is it clear to all of you? Can I move forward?
Yes, ma'am.
Right. So I'll stop share and I will go to my PowerPoint. Okay, so this is what is explained here and this is what is shown here. So here with the gender into medicine, this is the interaction effect. Now, when your interaction effect is there or is present, then you have to do a simple test. like how we did the earlier, no, BDI into medicine, the first ANOVA we performed. Same way, the first ANOVA we performed, you will get this kind of a result. So here it shows that your p-value is 0.019 and your degrees of freedom is 3 and error is 42. See how they have written here. The mean BDI score were affected by medicine. F within bracket 3. What is 3? 3 is the degree of freedom of medicine, followed by comma 42, which is the degree of freedom of the error, equal to the F value of medicine, 3.68. And your p-value is 0.019. So this is the way of interpreting. Okay, post-hoc also they have interpreted. Okay, so now we are going to go to MANOVA. Okay, MANOVA. So M followed by ANOVA. ANOVA is analysis of variance. M is multiple. So multiple ANOVA or multi-ANOVA is called as MANOVA. What do you mean by that? See, in ANOVA, we used one independent, one dependent. In factorial ANOVA, we used two independent and one dependent. In MANOVA, you can use more than one dependent variable. Okay, in MANOVA, you can use more than one dependent variable. So what does it mean? It is an ANOVA with several dependent variables. And here the purpose is to find out if the dependent variable can be changed by manipulating the independent variable. So we are trying to find out, can we make alterations in the dependent variable based on the independent variable? So this advantage is that you can do individual ANOVA together. The next one is you can protect against type 1 error. What is type 1 error? Rejecting the null hypothesis when it is actually true. Okay, when it is actually true. So that can be avoided when you do MANOVA. Here, one important thing that you should keep in mind is the two dependent variables or more than two dependent variables that you are using in your MANOVA test should not be correlated with each other. Okay, should not be correlated with each other. So there should not be any multicollinearity between the dependent variables. So how this actually functions or does is it creates a new dependent variable, which is a combination of multiple independent variables. And then it compares this particular new dependent variable with the different groups and finds out whether it is significantly different or not. So that is the procedure adopted for MANOVA. Coming to the assumptions of MANOVA, the first one is common, which we already spoke about. We spoke about it till normality. Okay, so the last but third, there is a linear relationship between each pair of dependent variables for each group of independent variable. So between one independent and one dependent variable, there should be a linear relationship. Okay, there should be homogeneity of variance covariance matrices and there should be no multicollinearity. So they should not be correlated with each other. So homogeneity of variance should be there. So that is the different assumptions for MANOVA. Now we are going to perform MANOVA on a file called as MANOVA itself, which comprises of job category, department, age, salary, increment, and job satisfaction. And we are going to put in the dependent variable increment and salary. And we are going to put in the dependent variable job category. Okay, let's open the file. I'll stop sharing this. I will go to MANOVA. Right. Okay, so see here, you have job category, you have department, you have age, salary, increment, and employee satisfaction. So these are the last three. Age, age is also a continuous variable. Department is a salary is a continuous variable. Increment is a continuous variable. Employee satisfaction also is a continuous variable. So the department is a categorical variable. Job category is a categorical variable. So see the variable view, job category. Okay, it's not mentioned here. Okay, forget. Okay, so now go to, where is analyze? Analyze. General linear model, multivariate. Why we are going to multivariate? Because we are using two dependent variables. When you have more than one dependent variable, you have to use multivariate. If it is less than two dependent variables, then you can use univariate. So go to multivariate. I'll just come back. So now I'm going to put salary, increment. I can also try out with employee. Let me put only two. Then job category into fixed factors. Go to plots, horizontal, add, continue, post-doc, QP, continue, options, job category. Here you have to choose descriptive statistics, estimates of effect size, homogeneity test. Okay, descriptive statistics, estimates of effect size, homogeneity test. Click on continue. Okay, is it clear? Should I repeat it again?
It's clear, ma'am.
Right. So I'll click on OK. I will stop sharing and I will open my output file. Right. So we got this particular output here. The first table shows you the number of participants in the different number of employees in the different job categories. Then in the descriptive statistics, it shows a breakup. It's like a cross-tab table between salary and job category, increment and job category. Then this is the box test of equality. So to find out whether the covariances of the dependent variables are equal across groups. So when it is significant, it means it is not equal. Okay, when p-value is significant, it means it is not equal. Then coming to multivariate test. So in this multivariate test, you should look at the Wilk lambda value. Okay, Wilk lambda value. So going down on the Wilk lambda value, you see the significant value is less than 0.05. So it is significant, which means there is a significant difference between the means of the salary or increment among the different job categories. Okay, among the different job categories. The first one is the intercept. You have to see the job category Wilks lambda. Okay, you have to see the job category Wilks lambda, not the intercept. The first one is intercept, which means constant. You have to see the job category. Here it is 9 here the significant value is less than 0.05. The F value is 108. Okay, the F value is 108. And the Wilks lambda value is 0.467. Okay, 0.467. And there is another value which is called as partial ETA squared. Now, this partial ETA square measures the effect, okay, measures the effect of the difference. Is the difference high, low, medium? That is what it measures. If it is anywhere above 0.15, then it can be considered as it can be considered as high. So that is the Wilks lambda value. Coming down, you have the Levin's test of equality that is greater than 0.05. So it is, that assumption is satisfied. Then coming to the test of between subject effect. So in this, you check your job category. So the same thing, here the F value is there, significant value is there. For increment, it is not significant. Okay, for increment, it is not significant. Only salary with the job category is significant. So it means that there is a significant difference in the means of the salary among the different job categories. But there is no significant difference in the means of the increment of the employee among the different job categories. Okay, the partial value, ETA square value is, for salary, you find the effect is high. Whereas for increment, you don't find the effect is high because it is not significant at all. Okay, right. So in estimated marginal means, you find the means, you find that the salary level for group 1 category is less. For group 2, it is slightly higher. For group 3, it is even more higher. Whereas the increment value is more or less the same for all the 3 job categories. That is why it was found not to be significant. So here in salary, see the p-value in this job category post-hoc test, you find that the salary of all the different job categories are different. 1 with 2, 1 with 3, 2 with 1, 2 with 3. So everywhere there is a significant difference. So it means that each job category is totally different in terms of its salary means. Okay. So coming down to the profile plot, you find that the salary increases among all categories. For job 1, it is less. For job 2, it is slightly higher. For job 3, it is even more higher. Then coming to the increment, you find a V shape here, which means that the increment for group 1 category is around 1612. But for group 2, it is 1611. So it's not a great difference, probably 1 rupee difference. That's all. Okay, so that is the difference you find. So that is why it did not come as significant in our result or in our output. Is it clear? Anything you would like me to explain again?
It's clear, ma'am.
Okay. So this is how we did this. So this is the interpretation of the table. So you have to check the mean in the descriptive table. In the multivariate table, you have to check the Wilk lambda value and write the Wilk lambda value here and the partial ETA value, partial effect value here. Then between the job category effects, which job category is different from which job category, you have to check. Okay, coming down to the next test, which is called as Anova. So what is this Anova? Anova we have seen, that is analysis of variance. What is this Anova? Anova is analysis of covariance. Okay, analysis of covariance. What does this covariance mean? See, in our test, okay, in our test, we might be having 4 or 5 variables. Now, we might not be using a particular variable in the test, but we want it to be controlled. I will give you a further explanation. Let's take the gym example. Okay. So your weight after 6 months, okay, your weight after 6 months in the gym, after 6 months after joining the gym, is it dependent on your previous weight or not? Did you get my question? See, supposing your weight before you hit the gym was 70. After hitting the gym, after 6 months, it has come down to 50 or 60. Now, this 60 or 50 value, that is your weight after you join the gym, Is it affected, is it influenced or affected by your previous weight value?
No, ma'am.
No or yes?
No.
Why?
Why? Because after he joined that gym, no, ma'am.
Hmm.
In that period, he used some diet and doing exercise.
Hmm.
So that weight is not affect this weight, no, ma'am.
I will rephrase in some other way. See, for example, a person before he joined the gym, he was 150 kgs. Okay. And another person who joined the gym was 70 kgs. Both are in the age group of 25. Okay. Both are in the age group of 25. Now, who will lose more weight?
That 150 kg.
Why he will lose more weight?
Already his BMI is more than that. That is why, ma'am.
Okay, because when you are more, when your weight is much higher than your normal index, okay, normal weight level, then your reduction will be very high. But if your current weight is somewhere close to your close to your normal weight or your expected weight, then your reduction will be less. So in both the cases, what is influencing your previous weight is influencing how much weight loss is going to happen after you join the gym. Correct?
Yes, ma'am. Yes, ma'am. Now it's understood. Yeah.
Okay. So now your previous weight influences your current weight. But I want to control that previous weight. I don't want to influence the new weight. So I want to control the previous weight and try to do a test. So for which you have to use a test called as Anova. Okay, for which you have to use a test called as Anova. You are controlling, when we say covariance, we are trying to control one particular, the effect of one particular variable on the dependent variable. Okay, you're trying to control one particular variable's effect on the dependent variable and try to see the influence of some other factor on the dependent variable. Okay, see here, the one-way ANCOVA has an additional benefit of allowing you to statistically control for a third variable, which you believe will affect your results. This third variable that could be affecting your results is called the covariate. Okay, that is called the covariate, and you should include it in your one-way ANCOVA analysis. Okay, right. So the database comprises of ID, sex, birth date, pre-diastolic pressure, pre-systolic pressure, treatment, post-systolic pressure, post-diastolic pressure. So here we are trying to see whether there is a significant difference in the adjusted means of the post-diastolic pressure among the different treatments by controlling the pre-diastolic pressure. Okay, so your covariate here is pre-diastolic pressure. By controlling the effect of pre-diastolic pressure, I am trying to study if there is a significant difference in the adjusted means of post-diastolic pressure among the different treatments. Okay, right. So let us see. So the assumptions here is they should be independent observations. Normality should be there, homogeneity should be there. The regression slope, okay, the regression slope also should have homogeneity, which means the beta coefficient for the covariate must be equal among all the subpopulations, and there should be a linear relationship between the covariate and the dependent variable. So how to do it? Go to analyze, general linear model, univariate. Then we have to put under dependent variable diastolic blood pressure, fixed factors, treatment. And in the covariate, you put diastolic blood pressure pre, not post, pre. Okay. Then coming down to options, you have to, in the estimated marginal options, put treatment. Click on descriptive statistics, estimates of effect size, homogeneity test also you can put. Okay, right. So let's stop here, go to SPSS, open the file, Anova. Okay, so I got my file. Is it visible? SPSS is visible?
Yes, ma'am.
Right. Okay, so let's start doing it. Here you have ID, sex, birth date, pre-diastolic pressure, pre-systolic pressure, treatment, post-diastolic pressure, post-systolic pressure. So we are going to control the pre-diastolic pressure by putting it as a covariate, and we are going to see how the post-diastolic pressure varies among the different treatment groups. Okay, so this is the objective of the study. So go to analyze general linear model, univariate. Why univariate? Because we have only one dependent variable. What is a dependent variable? It is the after treatment, post diastolic pressure after treatment. Fixed factor is treatment. Diastolic pressure before treatment is coming here. Okay, go to plots, treatment, add, continue, post hoc, treatment, TUP, continue, options, treatment, descriptive, estimate of effect size, homogeneity test, continue, click on OK. Is it clear? You want me to repeat again? Is it clear? Can I move forward?
Yes, ma'am.
Okay, I will share my output table. I made a mistake. I should not have given this. Descriptive statistics, I should not have ticked. Okay, just ignore that. Come to Levin's test of equality. So the Levin's test of equality is 0.002. So it is lesser than 0.05. So it is significant, which means that there is no equality of variance between the groups. Okay, then next is test of between subjects effect. So here you see the treatment. Okay, here you see the treatment. So in the treatment, you find the significant value is lesser than 0.05. So it means that your post diastolic pressure is different for different treatments. Okay, the F value is important. The degrees of freedom for treatment and the error term is also important. So all this you have to write in your interpretation. So coming to, this is not required, estimated marginal means. So you find what is the mean diastolic pressure for the different treatments here. So 95 for none, which is higher than 93, 92, 94. We found it also to be significant. Okay, we found it to be significant. Then coming to the post-hoc treatment, you find that there is no significant difference. Okay, there is a significant difference between none and old medicine. Okay, that is the only significant difference between the groups. None and old medicine are totally different from each other. See the different groups. So you find that old medicine is different from others. Okay, old medicine is different from others. By the value only you will be able to check. Okay, is the interpretation clear to all of you? So check the mean and the descriptive statistics. Check the treatment row in the test of between subjects. Check the adjusted means in the estimated table. Post-hoc test will be able to compare, pairwise comparison. So this is what the treatment. So you have to find a significant treatment effect was found. F is equal to F into in the brackets 3, 115 is equal to 8.19. P value is less than 0.00. The partial ETA square is 0.18. So this 0.18 or the ETA square value shows you what is the impact, what is the effect of difference between the different groups of treatment in terms of post-diastolic pressure. So this mean value is the adjusted means. Okay, this mean value is the adjusted means for covariate. Okay, so taking into consideration and controlling the covariate, this is the mean of the diastolic blood pressure for different treatments. Right. So next, coming to, if you have two independent variables rather than one, you are going to do a two-way maneuver. If you have one independent variable and one continuous covariate, you do a mancova. If you have one independent variable which consists of repeated measures, then you use one-way repeated measures, manova. So mancova is ancova into multiple times, or multiple ancova is called as mancova. It is a statistical technique that is an extension of ancova. So in mancova, we assess the statistical differences of several dependent variables by an independent grouping variable while controlling for a third variable called the covariate. Sometimes you can also use multiple covariates. Okay, so with this, we come to the end of the session. Is there any questions? Any doubts in anything that we covered today?
Yes, ma'am. Actually, we learned this. Already we know Anova, but these are the new things for us, ma'am.
Okay.
Yeah. Thank you, ma'am.
Right. Any other doubts related to the topic? Anything you didn't understand? Anything you want me to repeat?